Now we will take a look at different measurements of different measurements, scoring technique, or algorithm that allow us to perform link prediction. As you have already know from the earlier slide, that our aim is to identify the most likely link. That means we need to have some score that will allow us to connect the two nodes together. So the first technique is called, we use the local measurement, right? Measure the similarity locally. Locally means that at the node level. Local measurement here will predict the link based on the contact structure, whether that node contact with another node, how dense it is, how close it is in certain aspects. Okay. So the main idea, first idea here is to close the triangle, to close the transitivity between the two nodes. For example, if in this graph, which of the node do you think should be connected? Right? Which of the nodes should be connected? Should it be here? Should it be here, or red and purple? Or of which node should be connected? Right? Which one? Red and green. Right? Red and green is fine. Actually, blue and blue is also fine. So yeah, red and green should be connected. But why? Right? One justification should be that because they share a lot of friends, right? Just like in social network, when you have a lot of friends, you can use that as a ranking, right? Right now Facebook call it the mutual friends. If you have a lot of mutual friends, the list should be suggested earlier. So it means that you can just rank the number of mutual friends and then rank them. But there is actually a technique in link prediction that do just like that. That technique is called common neighbors. Right? In common neighbors, the technique would try to pick out the two nodes, unlinked nodes, the two unlinked nodes that share the most common neighbors. Right? So suppose we have nx as a set of neighbor of node x and ny a set of neighbor of node y. Then the similarity between x and y would be the intersection, the size of the intersection between the two. That means so the basic explanation, the simplest explanation for this one is friend of friend, right? We want to find the mutual friends, how many mutual friends that we have. Okay, so for this example, you can see that I obviously refrain from blue and blue, because actually blue and blue would compete with the red and green here. They have equal score, so that means they are equally likely to be suggested. So but for the red one, right, the red and so for red and green share two here, right? Two neighbors come from the set of neighbor of red would be the two blue. The set of neighbor of blue or of green would be two blue and the purple. But the intersection between them give you only red and green. So the common neighbor would be two, right? For the first. For the second one, red and purple, right? You can see that both share no common neighbors, so that it will make this equal 0. For green and this one, that should not be considered here, because they should not be considered because they are linked already. Right? For blue and purple, right? Share only one node here. Right? So, but you can see that here the blue itself, I mean this blue, okay, or this blue or whatever, right? But they itself contains two neighbor, red and green. Why this one contains only green, but intersection give you one, right? This is common neighbor. Okay. All right. For the common neighbor implementation so for this one we will pick that, okay, these should be connected. That means suppose we are working as a create application, you want to add friends here, we can just suggest the one that have the highest common neighbor, or this one would be fine as well. That means suppose you decide to create a social network app. For example, if the university create, well, right now we have the LEB2, but if for somehow you want to create something like the connection, you want to create a chat system, this is the way that would allow us to link the authors. Just let them link themselves, right? They can link friends and they will see something with of their friends. Yeah, you now have social network system there. Okay, let's take a look at Python. Let me open Python. All right, already done that. Switch the share to here. All right. Okay, I use the Dolphin edges because it contains smaller network and it's easier to see and compute, right? So let's first load data, load it as CSV, so that I have A here as the link between two Dolphin, different names, right? And then convert it into the to the graph. Drawing that, we get this one. This graph will show you that there are certain connections, there are certain hubs, and it kind of express the preferential attachment that there are hubs in the network. And if we were to plot the degree distribution of this one, you will probably see the preferential attachment way there. Okay, so if we want to, well, find a pair, let's say you want to find a pair of dolphin and let them make friends, maybe creating a stronger bond between this. How do we do that? Right? The study itself is from dolphin, not in the aquarium or so it's hard to bring together. But let's see. So what we want to find the two compatible one. Okay, think about them as people then. Then we can use this, right? We can use the function called common neighbor. So this common neighbor function is actually counting the number of mutual friends, just like that. This is for the network X. For the graph X, it also contains similar function. You can take find the function itself, but you can see that it's just the intersection between the neighbors. So first, suppose you want to implement that, you need to identify neighbors of each node, then intersect them. Then you get the common neighbor here. Right. For this one, I extract the none edges. None edges function for the network X will give you the list of none edges, right? The other pair that are not edges. And then from that target, which is an iterator used once and then it's gone, you need, we create a for loop here in the initialization. And each of these we use it as E1 and E0 and E1 here, and then find the common neighbor of E0 and E1 in the graph G. Okay. And sort them based on the second elements of the list. Why is that? Actually, this come from the results here. We want to use the third column here, but it's not data frame yet. It's the list of a list. So to sort the list of a list there, you need to use the sorted function, the basic Python function, and you can give the keys, which we say that is this elements, and reverse true means that the first would be those that are closely, those have high value. Right? So in this case, mean that those that have potential to be connected because they share a lot of friends. Okay? They share a lot of mutual friends. Okay, this is the first way. Right? So you can see that the basic social net analysis is quite simple. Like just from the last time that we take a look at the way to analyze the the degree, right? Degree centrality is also simple. Just 5 people who have mostly connected. And there are also other aspects of the way that you can utilize in network analysis as well. This as well. To identify the links, you can just take a look at the mutual friends, and then we get those that should be linked. Like for Jet, maybe these two. Like for Hook, should be Stripes, and so on. Right? We would have the list here. Okay, let me switch back here. So this is the graph, and just like the common neighbor, you get the common neighbor of the graph. Okay, that's the first one. Now let's take a look at the second one. The second one is also similar to the first one, but there is one key difference, that is Checkhard coefficient. Instead of looking at the intersection or the common neighbor between them, it also normalize the relationship by the number of connections as well. What does it mean? It means that if you connect to one node and that node is a hub, right? That node is a hub. It will contain lots of neighbor, and a lot of neighbor would means that this connection itself is not closely connected. It's not like it's not personal. You are just connecting to people that also connecting a lot to others. So Checkcard normalize that by find the union of the two set. And by finding the union of the two set, you have the total connection out. Right. So let's compare the importance in terms of the connections between red and green and blue. Now we can tell apart which one is better connected than which. Okay. So from this definition of the Checkhard coefficient, we need to the red and green would have the values of 2/3. Okay, 2 from the two node here, that when both intersects that you have equal 2. For 3, this comes from the union of the elements, neighbor elements, which are these 3 nodes. So we have the coefficient here equal 0.667. Why? For this one, right? This one, the 2 here are both connected to these 2. That means these 2 are very similar, right? The blue and the blue here, they are very similar because they are similar in terms of the mutual connection. They both connect to this group. That means these 2 should be connected, right? That's why we have that. And yeah, we should suggest this link out. Okay, and now if we compare to other nodes, like we compare this to this one, well, you can see that, well, these 2 share one node. The total number of neighbors equal 2, so that means 0.5, even less than the red and green, right? Now let's take a look at this one and this one. It also share one node, but also 0.5, right? This node and this node, 0.5. So you can see that if the nodes are not close to one another, then the link should not be suggested there. So you can see that both common neighbors and Checkhard coefficients rely on similar measurements, the common connection between the 2. And from this, you see that this look like recommender system, right? This looks just like recommender system. That is, if you watch these 2 movies together, maybe you want to watch another, or maybe you are close to another. So you can see that they are quite similar in terms of the concept here. Okay, so this is a Checkhard coefficient, right? And right, switch. Take a look at that. Okay, so for common neighbor, we see that Jet and a bank should be connected. Jet and SN 90 should be connected. Z is here, right? And Z is a hub, and so there are other links that have not been connected to this one yet, and then we find it by doing this. Right. For the Checkcard coefficient, here is a function again, Checkcard coefficient, and Checkcard coefficient would list the Checkcard coefficient of each node. Right. It lists the Checkcard coefficient of each node here. Problem is, this is the Checkcard coefficient of the whole data set, of the whole graph. That means we need to also filter it out to see which one should connect to which. Maybe they are already connected here. Right? So at least we see that Z and SN90 here, and we will take a look at here. You can see that Z and SN90 have the coefficient of 0.4. And the others are ranked down. Z and upbank now it's not 4. Right? Here it's 4. But here you can see that, well, now we have ranks based on the closeness that it should be close to the kind of the common elements between the two normalized by the number of connections. Okay, let's switch. Right. Now the third one, right? The third one is resource allocation. Resource allocation is not the course that you learned last semester. It's not the resource allocation by Ajahn Ming and Ajahn Pon, right? Resource allocation is a measurement, right, that measure again, but it's measure the what to say? It measures the degree, but the name is resource allocation. It's measure the similarity between nodes. But instead of looking at the common elements between them, resource allocation measure by find the degree, right? These are the summation of the 1 over the degrees, means that if that nodes connect to a lot of people, it will have less value. If that node connect to just a few, it will have high value. And then it would compute the resource allocation score by looking at the intersection between the two nodes. So earlier, if we go back to the common neighbor, it's like this, it's like resource allocation, but instead of having 1 over the degree, you have just score of 1. If you have common neighbor, you sum it with a score of 1. But with this one, it depends, the intersection is the same as in the first example, as in common neighbor. But the summation here is not all 1. The summation is 1 over the degree of the node in the intersection. That means if the node in the intersection contains a lot of connection, it will have low value. If the node in the connection, in the sharing between them, just contains just few nodes, then it will have high values. So the meaning here is that if we share the neighbor with low degree, then it matters more. But if we share the connection through hub, then it's meaningless, right? That means in terms of the connection. So you can imagine here, if you are connected to a person through some directory, right, through some directory, that means like you are connecting with a person through workplace. That means the workplace connect to a lot of people, right? That means the connection might not be close. But if you connect to that person from some restaurant, from some place that have not have a lot of degree, then it means that that connection would kind of express a lot more similarity between two nodes. And that's the idea of this resource allocation measurement. That means from our network here, if you compare red and green, comparing to blue and blue, which one has higher degree of resource allocation? Right? Which one? red and green, and blue and blue. Which one has higher resource allocation? Which one? We have answer coming in. Right, blue and blue. Okay. Right. Green, blue. let's look. Red and green, right? Red and green, red and green. The common neighbor between red and greens are blue and blue, right? This blue has the degrees of 2, okay? This blue had the degree of 2. That means the combination here will be 1/2 and 1/2. That equals 1. For the blue and blue, right? This one, these are 2 common connection. The red one, well, this is 1/2, but this one is 1/3. That means it has a value of 0.83. And you can see that the connection should be formed here. So this is like the count of the close connection, right? If you connect two person to small connection, it meaning much more than connection to crowded connection. All right. Again, switch back to Python. Okay. Resource allocation. Okay. So here resource allocation and then rank by that. You can see that for this, the first one coming up is the connection between jet and notch. Right? Let's focus just on jet because he's easier to see in the graph. So you can see that jet and notch come first, not jet and SN90 or jet and up bank, but jet and notch. But in this in common neighbor, jet and notch come in the 4th place. Okay, 3rd or 4th place. In Checkcard coefficient, jet and notch come in down here, the 3rd place or the 2nd place. But in resource allocation, it comes up first. Why is that? We need to take a look. Jet and notch. Is the connection from this can be seen as because jet and notch are connected to just a node that connect to just these two, right? So it means that these two should be connected. Right? There should be a connection between this because it's personally connected to this one. So this connection would be suggested, right? Okay. Now let's again look at the pair technique. I try to bring it. Actually, there are plenty more techniques of link prediction. I chose 4 of them because they are quite comparable to one another. Like when we take a look at common neighbor, comparing to the Checkhard coefficient, you can see that they are quite similar. When we look at resource allocation and the atomic Adar index here, also similar to one another. In the atomic Adar index, the authors try to solve the problems of the size of the degree. What is that? In this equation, if you remember that usually in social network, the degrees of the network would obey power laws, right? That means a lot of them would have a lot of them would have low degree, while some of them would have high degree. When you have high degree, this score would be almost 0. If you have a very high degree, it would be 0. And the growth of the value itself in the power laws, it's like this one. It's like this, right? Power laws. But because here, the growth of the value in this direction would be in exponential terms. That is, in few nodes that you have. If you have those few nodes in a very large value, then the degree itself would be the contribution here would be almost zero. And it's kind of unfair because you kind of giving the node at the low connection more chance to connect than the node at the high connection. So to address that, Adamic ADA index utilize just put the logarithmic here in the degree to convert from exponential growth to linear growth. That means the exponential growth we see here, I already shared that, okay. Exponential we see here would be converted into a linear growth by taking log here. Okay, so it linearized the linearize the value and reduce the hub effects in the computation here. Okay, switch to Adamic ADA. Run it. Right, so if you take a look at the values, right? The values here is kind of normalized, but you can see that it's from 0.9 to some values down there, because it's kind of 1 and over some values. But while for this one, we have actually, if you take a look at this, the rank is quite similar. Jet and Notch come at the third one, but here Jet and Notch come at the fourth one. The rank switch a bit. Some that have like some that connect to high connectivity nodes, but kind of become better ranked, right? Which one? So the N16, the N. Oh, this up bank and feather, right? Now kind of goes up in the rank. Right? This one up bank and feather here, probably because it's connected to the highly connected node. Okay. So here, these are the 4 techniques that allow you to perform link prediction. It can be used to make prediction based on the local structure. And I would say that most of application utilize this one because it's simplest, and it also allow you to connect to especially in the social network, to allow a person to connect to another person that share a lot of connection, which makes sense, right? Make very sense there. Okay. Now that's the local scale. Okay. Let's take a look at this global scale. And once we take a look at this one at global scale, we take a few short minutes break and then come back to take a look at the another approach, the matrix decomposition approach, instead of the similarity approach to perform link prediction. Okay. In terms of the global aspects, instead of focusing on just one node, connecting to all other nodes around them, right? We trying to find a global structure, the whole adjacency matrix, and that from that adjacency matrix, we would find a connection between them. But actually, the two are compatible. It's just that instead of doing it one by one, you are using the whole structure of the network to compute. So it can be done by like finding the shortest path between each node. Right? If you can find the shortest path between each node, then you can calculate the distance between them. Right. So for example, in the global scale, if we compare to local scale, well, if we have the adjacency matrix A, when you do the A square, you get common neighbors, just like that. Just multiply A with A, then you get the common neighbor between them. If you remember in the graph, when you have the graph, when you square the graph, you get the two-step traversal. That is, you traverse from one point to another point and to another point, right, in the graph. So that's the two-step traversal. For example, if I draw a graph like this one, let me change the say A, let me. Well, I can use that to write, probably. Um, stop. Okay, let me make a notation. How can I make a notation? Annotation. Okay, there's a feedback here. Right, if you have a connection like this one, and let's make it one direction. What else? Okay, in terms of the adjacency matrix of this, the adjacency matrix would look like this one. For A, B, C, D, A transits to C, that means we have like this. B go to A and D. And C go to D. And finally, D goes to nowhere. Okay, this is A. So in terms of common neighbor, right? Here it said that common neighbor is A square. So if we to calculate A square is to multiply A with A. So I would just multiply the row with the column, right? Multiplying the row here. Multiplying the row here with the column, with each column. Okay. So here I would just multiply the first row with the first column and get 0. First row with the second column, 0 again. First row with the third, also 0. The first row with the last column, get 1. Okay. The second row with the first, second, 0, 0. But with the third one, get 1 and 0. And the third one, all 0. The last one, all 0. Okay, this is A square, right? From A square, now we have the adjacency matrix of A square. And if we take a look at that A square, now we see that there's a connection here. Let me just turn it off. Okay. Okay. You can see that from this, the A square, it shows you that there should be connection between A and D, right? A and D. And from this one, you see that A and D is like this. It's like there should be a connection between A and D. And there should be a connection between B and C. Right? So by square the matrix, you now have the two-step movement. And in the two-step movement, it gives you the link that should be there. Okay, so this is for just the graph here, and then you see that by looking at the global scale, we can just identify all the node that should connect in the common neighbor here, right? Oh, let me clear it out. Clear all drawing. right? And there are different way to uh, to form this connection, right? In discrete mathematics, if you remember in the first year, there are techniques that you learn but you don't know why you learn it, right? The techniques called closure in discrete mathematics, graph theories. Actually, it's on the relation. I think I taught that maybe back 3 or 4 years ago. In that topics, it talk about you can find the closure of relation. The closure of relation is the kind of the relation that should be there with respect to certain properties. Okay, with similar technique, we can extend from just finding the two movement to the three movement, but instead of having to let the weight to be the same as the existing, we can just square it and then weight it by the decreasing weight. So alpha, let's think about alpha when you do something like exponential smoothing. Alpha would reflect something like the value itself that should be there. It will reflect like the decrease of the weight that you want it to be for the previous example. So for that one, we can square it and then divide it by the factorial. Factorial will go faster than the square above here, so the weight will be decreased. And we can combine it by different layers. That means you have the similarity that the two should be connected to two steps, three steps, and further, depending on the application that you try to find a connection between them. Okay. So the basic is like common connection like this one, but it can be modified further to include like something like exponential smoothing here. Okay. So the key points in the link prediction algorithm, the basic one, is that you can use this technique to identify the links for sure. However, you can see that different links prediction technique would have different natures, and it depends on the graph. It depends on the types of the graph that you want to use. So that means you need to understand the behavior of the graph first. For example, if we talk about bipartite graph, right? Bipartite graph is a graph that you have two parts. Just like if you do if we talk about LinkedIn, right? In LinkedIn, you would have the graph on the left-hand side as people, and the graph on the right-hand side as job. And then some of the people may look at the job, some may not. Now you want to know whether you should recommend some job like this one to this person or not, or this job to this person or not. You can see that the graph is bipartite, have two parts. That means the connection cannot be just, if you just square the matrix, what would happen? It would mean just the movement of one node to another node, right? Just two steps, which is fine if you want to find the connection with the job to the person. But if you want to create a connection between people here, you want to create a network. But you can see that because the nature of bipartite graph, that is, you cannot have connection, right? You cannot have the existing connection at first. So if you have bipartite graph like this, to find that this one connect to this one, it need to go through the three steps, right? Go to here and here. That means you cannot use just a square. You need to use a cube, right? A to the 3, right? In order of the global index here, of the global method here, to find the transition from this person to this person. Once that's done, you have connection between them. Okay. But for sure, you can use the other technique like common neighbor if there exists the connection between them already. You can use some mutual friends to do that. But for application like LinkedIn, there exists a connection for sure. You can use that as a score. But you can also use this two-step relationship to identify the connection between them. Okay, so that means algorithms that you choose to use depends on the nature of the graph. Different graphs grow on different mechanisms. Understanding the behavior of the graph, the evolution of the graph, takes precedence than selecting algorithms. You need to understand how the graph is generated first. Once you know that, you will be able to pick the algorithm that will work better on specific one. The one that I showed you there, those are algorithms that are suitable for the scale-free graph, the graph that have hubs, the social network graph. But if you have specific graph that have more than one layers, then need to be tuned up a bit, uh, like just finding neighbor here would not okay. You might want to find the sharing topics and then come back there. Okay.